All right, so you'll be glad you're here.
Yeah.
Or stay the year problem. Well, until you get it. And then once you get it, it's probably one of the easiest days of the year. So keep that in mind. If you keep in mind that this is going to be easy, once you get what you're doing, it'll relieve the pain of maybe it's how it's a little confusing now. So what we're trying to do here, I'm going to explain all the why, and then when I show you the how, you'll go, oh, that's it. So what we're trying to do here is figure out what derivatives of inverse functions are. Yesterday, if you remember, we learned formulas to do derivatives of inverse trig functions. There's no formula for every function in the world. So for every other inverse function, you've got to actually have a process. And you could use this process on trig functions as well, which I'll show you in case you forget what the formulas are. You could bail yourself out with this. But if you know the formulas for inverse trig functions, it makes it really easy. But we'll run into a problem at the end, and you'll see that with the sine curve. So here is the way I'm going to just start you with a formula, and then I'm going to kind of work backwards a little bit. So here is your formula right here for finding the derivative of an inverse of f. And you can see it's kind of confusing looking. Everybody with me? Yeah. Okay, so look, the derivative of the inverse of a function is equal to the reciprocal of the derivative of the regular function of the inverse function of x. And that sounds like a mouthful, and it's like confusing. And every year, I'll be honest with you, I have to rethink this. Now, if you're a proof person, I can show you how to do the proof of this real quickly, and you won't forget it. But honestly, I don't know that you really need this to be able to do most of the problems you're going to do. Let me show you. So here would be the proof of this. Do you remember, and if you don't, no worries, but literally the definition of a function, how do you check if a function and its inverse are actually inverses? It's if f of f inverse of x gives you x, then you know that f and f inverse are inverses. Well, if that's a true statement, if you know that that's true, then this is where this formula comes from. So notice right here, I'm starting with the function of the inverse of x gives me x. All right? Now, if I ddx both sides, which is what I did right here, I'm ddxing the left, right there, I'm ddxing the right. Do you remember how to take a derivative of a composite function? Remember how you start with the outside and you go f prime of blah? That's what I'm doing first. F prime of that. That gives you this part, takes care of the f. Then you take the derivative of the f inverse, right? So f inverse derivative of x, that takes care of that. And then, of course, the derivative of x is 1. So this is derivative of f of blah times the derivative of f inverse of blah times 1, and then the derivative of x is 1. So that's your formula. And then if I want the derivative of the inverse part, which is this, I just divide both sides by that. So you can see over here, I've divided both sides by that, and there's my formula. So should you ever forget it, all you really have to do is write down the inverse definition and take the derivative of both sides and solve for the derivative of the inverse. Now, a couple things you need to really know about derivatives, about inverses, and you probably remember this because I taught all of you Algebra 2, but you remember everything. So, do you remember that with functions, if you have an x and a y, that what do you do to find its inverse? Switch the x and the y. So what that means is, if you have any function, any value that you plug into a function spits out some other value, right? Well, if I switch the x and y's, doesn't that mean that on the inverse, any b you plugged in is going to give me an a? Because every point on a function is flipped on an inverse, and vice versa. Does that make sense? So if that's true, let's go back to our formula. Our formula is saying this. They want you to plug x into the derivative of the inverse. Now, at first glance, that doesn't seem like a big deal. How hard can it be to find the inverse function? We've been doing that for years, right? You switch the x and the y's, you resolve for the new y value in terms of x, and you get it. So really, that's all you have to do if you can do that. But what if you can't resolve? I'm now asking you to take the derivative. Well, that gets kind of messy, because when I take the derivative, I'm either going to have to use implicit differentiation, which is fine, but the big problem is I'm going to need to know a value that you get by plugging something into that function. For instance, if I ask you to plug in an x value in the inverse, that's like plugging b in to the inverse. That's the same thing as needing the a value in the original function. And if you look right here, what is this saying? This is saying whatever x value got plugged into the inverse, whatever got plugged into the inverse is going to give me a different value. So this is the same thing as, like, if this right here is this, then I got to replace it with the a. So like this problem is basically saying the derivative of the inverse at b is this. Let me just do it all the way for you. This is saying, go back and write this. If f of a is b, and f inverse of b is a. So if this is asking me to take a derivative of an inverse at b, where x is b, this is the same thing as me saying this. Because f inverse of b is what? A. So here's how I think that you ought to look at these. In the event I can't find the inverse function, that makes it really hard for me to actually take a derivative of it, plug stuff into it. So what I'm going to do is I'm going to use this. Because this means I don't have to take the derivative of the inverse. I can take the derivative of the what? Of just the f function. And the f function is normally what you're given. The only difference is taking the derivative of the f function and flipping it, I can't use that. I have to use the coordinate that would have gone with that. And to figure out what coordinate goes with that b, you have to go, oh, I need to figure out what value went with that, whether you have the function or the inverse. And that's where it gets a little tricky. Now, this process is explained a little bit more clearly in this picture. And I know there's a lot going on in this picture, so let me walk you through it. So this picture is a picture of the function f. You can see it go right here. And its inverse right there. And if you remember about f's and f inverses, they're always reciprocals about what? The y equals x line. So y equals x, you're going to see a mirror image there. Now I want you to look closely. If I asked you for the derivative, I'm pointing right here, the derivative of the inverse at a, here's the inverse function, there's a. And there's the point, right? AB, right there. There's your point AB. And you can see that the slope there looks like a half. Well, the derivative of the inverse at A ends up being what? The reciprocal, not 1/2, but 2, the reciprocal of the derivative of the regular function, but not at A, at B. Because the A and B's are switched. So the derivative of the inverse at A is the reciprocal of the derivative of the regular function at B, based on this picture. And the nice part about thinking this way is I don't have to take the derivative of the inverse function, which would probably require implicit differentiation, which is not a horrible deal, it's just time consuming. The thing that you have to be careful about is this. Most of the time, they're going to give you this information. They're going to ask you to take a derivative of the inverse at some x value called 3. But remember, that's the x value of the inverse. And the x value of the inverse is the same thing as the what? Y value on the regular function. So what you're trying to do is link this inverse to this regular function and make sure you understand that the a and the b are flipped. So what's going to happen is for you to find the derivative of the inverse at an a value, you're going to find the derivative of the regular function at the b value, the coordinate goes with that a, and then flip it. And you'll see that this process is not overwhelming, even though it looks a lot right here. Most people, after about the third example, go, oh, okay. So check it out. I'm scrolling up. I'm going to give you an example. So right here, I give you this random function, looks like a cubic function, and I go, hey, find the derivative of the inverse of that when x is 3. So essentially, I'm finding this, the derivative of the inverse of f. So most people go, oh, let me try to find the inverse function. So here's what happens when they try to find the inverse function. They change y to x. They change this y to an x, and they change these x's to y's. Now, I know it's hard, you're having a hard time seeing that, but anyway. When I do that, can you actually solve for y there? You can't. So it makes it harder to find the derivative because you have to implicitly differentiate. It gets a little messy. So here's what we're going to do. To find the derivative of the inverse at 3, we're going to find the derivative of the regular function, but not at 3, at whatever 3 would have gone with. And we're going to plug that into the derivative of this, which I'm seeing nice and clearly. So let's think for a second. How do I figure out what goes with that 3? Well, here's what I do. If I am using an x value of an inverse, and that x value is 3, that would be the same thing as what? 3 being the y value on my original function. So I'm going to plug 3 in for y in my original function and eyeball it. Now, I know you're like, eyeball it, that's a little sketchy. Well, the only way it wouldn't be sketchy is for me to do this, move the 3 over and pull out long division, and synthetic division, and guess and check, using all that stuff to see what my roots are. AP is not going to make you do that. In my experience, the numbers are always either 0, 1 or -1, 2 or -2. Occasionally get as high as 3 or -3, but I really haven't seen them higher than that. So I just think, okay, 3 on the inverse is the same thing, for an x, is the same thing as 3 as a y in their regular function. So let's figure out what that is. So eyeballing it, I plug a 1 in. That's not true. I plug a -1 in there. That didn't work. I plug a 2 in there. Ooh, it did work. So when x is 2 on the regular function, that's the same thing as plugging a 3 into the inverse gives me 2. Plugging a 2 into the regular function gives me 3. So that tells me I don't have to do this. I just have to find f inverse of 2, because that's the number that goes with that 3. That's not hard. What's the derivative of f? 3/4 x squared plus 1. Plug a 2 in. What do you get? So that gives me, the denominator gives me 4, and the flip it part is the fact that you have the denominator. Now your other option is to do this, and you can do it if you want. Your other option is to go, no, no, no. So to do this, I've got to take the derivative of the inverse function. Well, technically, watch this. The derivative of your inverse function is switch x and y. If I switch x and y, I would get this. And then I have to implicitly differentiate. All right, the derivative of the left side is 1. The derivative of that is 3/4 y squared dy dx plus 1 dy dx, and then 0. And then I factor out a dy dx out of that, and I get 3/4 y squared plus 1. And then I divide both sides. So when I divide both sides, what do you get? Doesn't that look familiar? Isn't that literally what I did on the other problem? On the other problem, I just found out that it was 2, and I took the derivative of f. What's the derivative of f? 3/4 x squared plus 1. Sorry, 3/4, not 3. 3/4 x squared plus 1, 3/4 y squared plus 1. The only difference is I'm taking the derivative of the original function. If you do it this way, you're taking the derivative of the inverse and plugging in that coordinate, but you still have to figure out what that value is, right? Because doing it this way, taking the derivative of the inverse and plugging a 3 in there, 3 is the x. I don't want the x now. I want the y, the number that goes with that 3. So you're still having to find it. So in my opinion, I guess to end this conversation and move on, using this derivative formula right here is not great. I say you skip that part and say the derivative of the inverse at that is the same thing as the derivative of the regular function at its matching coordinate flipped. And that way you can just take the derivative of the regular function and not deal with all that implicit junk, which was a bunch of extra steps. So let's look at another example. Here we go. Example 1. They're asking you for this. The derivative of the inverse. The derivative of the inverse at -3 is the same thing as the reciprocal of the derivative of the regular function, but not at -3, at -3's matching coordinate. So you think to yourself, well, what matches -3 on the inverse? A -3 x value on the inverse gives you something, and a regular function something gives you -3. So if I have the regular function, I'm going to plug -3 in for y, right? And figure out what that x is by eyeballing it. Unless I can solve. If I can solve, solve. I just don't know how to solve that with algebra without going into long division. So I do a little guessing. Does 1 work? Nope. Does -1 work? Actually, yes. -1 cubed minus 4 plus 2 is -3. So when x is -1, that works. What does that do? That confirms to me that I don't use -3. I'm going to use -1. So all you have to do now is take the derivative of the f, which is 3 blah squared plus 4. Plug the -1 in, and you get 1/7. And I'm recording all this. Let's try it again. Everybody got this at once? So let g is the, so that's the g function. G -1, g to the -1 denotes the inverse of g. What am I asking you for? The derivative of the inverse of g at 2. So we know from our little picture that the derivative of the inverse of g at a 2 is the same thing as the reciprocal of the derivative of the regular g function, but not at 2, at whatever coordinate went with 2 on that inverse. Right? So I think, well, a 2 into the inverse gives me something, just like a something into the regular function gives me a 2. Well, there's the regular function. So I'm going to plug 2, not in for x, but in for y, and solve for what x value that would be. Well, I don't know how to solve for that. So I start guessing and checking, and what do you notice? 1 works, doesn't it? So if x equal 1 works there, then we know that the x value in the original must have been the y value in the inverse. I want the x value in the original here. So all I have to do to figure this out now is what? Take the derivative of the g, 5x to the 4th, 5 blah to the 4th plus 3, flip it, and plug that 1 in. 1/8. And you'll notice that, look, anytime you have a 1/8, you almost always have an 8, because there's always somebody who forgets to flip it at the end. And if you're again thinking, why do I flip it? Remember the picture? The derivative of the inverse at one value was the same thing as the reciprocal of the derivative of the regular function at its corresponding coordinate. Let's do one more and then I'm going to be bored. Look at number 3. All right, so number 3. If f is that, find the value of ddx of f inverse of x. So that's, again, another way to write the derivative of the inverse of x at 2. So let's think. The derivative of the inverse at 2 is the same thing as the derivative of the regular function flipped, but not at 2, at the coordinate that goes with 2, because I'm going from an inverse to a regular function. Well, let's think about it. An inverse at 2 gives me something. A regular function at something gives me 2. So the regular function, when I plug something in for x, gives me 2. Well, I don't know how to solve this at all. So what do? I guess and check. And when I look at it, I plug a couple numbers in. Again, I'm checking 1, -1, 2, -2, 3, -3, but 1 works, doesn't it? X equal 1 works. So that would mean I need to use 1 anytime I'm dealing with a regular f, not an inverse. This is a regular f. Take the derivative, plug a 1 in. What's the derivative of that? 5x to the 4th plus 1. 5 blah to the 4th plus 1. And you plug the 1 in. And you get 1/6, right? Don't forget to flip. Seen it? Now, AP also likes to give you stuff. Like, look at number 5. Number 5, and number 5 is about as easy as you'd ever see it because they only gave you a minimal amount of information. They normally give you extra information to make it more confusing. So let me just walk you through it. What are they asking you for? The derivative of the inverse of f at 5. And we know that the derivative of the inverse of f at 5 is the same thing as what? The reciprocal of the derivative of the regular function, but not at 5, and whatever would go with that 5, right? So how do I play that out again? Well, if I'm plugging an inverse into a 5 into the inverse and getting a number, that'd be the same thing as plugging that number into the function and getting a 5. Oh, look. So what must that value be? So use a 4. Oh, look. Are you with me? So this is an example of one that's spoon-feeding you, and then 1 divided by 2/3 is 3/2. They're spoon-feeding the answer, but you know what they would normally have up here? They would normally have an f of 4 equals 5. They'd have an f of 7 equals 4. They'd have an f of 5 equals 10. They'd have an f in prime of 5 equals 1/7. They'd have all this other stuff to be confusing. And a lot of times people go, oh, f prime of 4, and they go grab this for the derivative. Or they're looking for, oh, wait a minute, if f of 4 is 5, they don't think to do this. They go and grab, oh, f5 is 10, and they use f prime of 10 or something like that. They give you this extra stuff to try to be confusing. This next one is slightly more confusing, but not that bad. Number 6, if the derivative of g, derivative at 3 is being asked for, we know that the derivative of the inverse of g of 3 is the same thing as 1 over the derivative of the regular function g, but not at 3, and whatever goes with that 3. So if an inverse of g of 3 gives me blank, then g of blank would give me 3. Look at that. That would mean that the 7 is the value that I need. And then sure enough, g prime of 7 is 3/4. And again, don't forget, if you flip a 3/4, you get a 4/3. But you'll notice 3/4 is certainly an option, isn't it? And look, it's out there at it's out there at A, just baiting you in. Seen it? Okay, let me jump around to a couple more and then we'll call it a day because, tables. You're going to be tabled to death on the AP test. My students are usually very prepared for those because we beat them into the ground. So you'll like them most of the time. But here we go, big table of values. You'll see that I'm asking you about F inverse and F. I gave you extra values like G just to be more confusing. Make sure you really know how to read a table. So look at this and make sure you can make sense of this. It's telling you that capital H of X is F inverse. So they're asking you for the derivative of H. So what are they really asking you for? The derivative of the inverse. So they're asking you for the derivative of H, but that means the derivative of the inverse of X at 3. Okay? But we know that the derivative of the inverse at 3 is the same thing as the derivative of the regular function. Not at 3, but what goes with 3. And so, since F inverse of 3 gives me something, what F of something gives me 3? Look at your table. What F of what gives me 3? 2. So that means I'm using 2. And then what's the derivative of F at 2? 1. And you get 1 over 1, which I got to be honest with you, probably never going to happen because the denominator is the same thing as the reciprocal. And they always want to give you a chance to mess that up. Forget to take the reciprocal and miss it. Here you would have gotten bailed out if you forgot to take the reciprocal. What about, we'll do number 10. It's kind of the same thing. But, H inverse. Anyway, let's try it with G. No, let's stick to it. So H of X equals F inverse of X. So I want the derivative of H, which is the same thing as what? The derivative of H is the inverse. It's the same, the derivative of the inverse at 1. And we know that the derivative of the inverse at 1, same thing as the reciprocal of the derivative of the regular function, but not at 1. Why? Because if I'm plugging 1 into the inverse, I'm getting something. That's like plugging that something into the F and getting 1. Where does that happen? At 0. So I'm going to use a 0. And what's F prime of 0? -1. And again, you can see here, if you forgot to take the reciprocal of -1, you still would have been right. That's probably not going to happen on a test. See it? Now let me show you a couple more that are unique. So jump to 13. So 13 is a sine function. Now I'm going to pretend that I don't know about an inverse function to show you that on your AP test, if you completely forget your definition of an inverse sine, you could still get it. So right here they're saying if F is this, then what is the derivative? And G is the inverse of F. So they're telling you G is the inverse of F. What's the derivative of G? Well, if G is the inverse of F, then I'm asking you what's the derivative of F at 1/2? I'm sorry, the derivative of F inverse at 1/2. So here we go. The derivative of the inverse of F at 1/2. Now, that's the same thing as 1 over the derivative of the regular function, but not at 1/2, at whatever would go with 1/2. So how do you think through this? Remember, an F inverse of 1/2 gives me something. That means an F of something gives me 1/2. Well, where's my F of something? There it is. So answer this question. If I plug a 1/2 in for Y, what X value do I get? Where is sine of X equal to 1/2? And remember, we don't have degrees. Got to know your unit circle. Or know your definition of the inverse derivative. Pi over 6, so 30 degrees. At 30 degrees, you're up 1/2, right? Pi over 6. So that means X would be pi over 6 there. So right here, pi over 6. So here's what I want to do. Pi over 6. Can you take the derivative of F? What is it? Cosine? Plug the pi over 6 in and flip it. What's cosine of pi over 6? Square root of 3 over 2. What's the reciprocal of square root of 3 over 2? 2 over root 3 must be a. We don't rationalize, don't need to. Now, did you notice that I just did the derivative of the inverse of sine without the formula? All right? Now, watch with the formula. Remember, that's my answer. Another thing I could do, which is a lot easier, I think, is wait. If I want the derivative of the inverse of that, that's the same thing as me ddxing an arctan at 1/2. Isn't it? Sorry.
Did I miss something yesterday?
No, sorry. Arc sine at x is 1/2. What's my formula for the derivative of arc sine? The square root of 1 minus what? X squared, or u squared. The derivative of the u on the top. Plug in your x value. Now, if you're looking at that, looking at your answer and going, how is that going to give me the same thing? Do the math. 1 minus 1/4 is what? Square root of 3/4 is? Square root of 3 over 2, flip it. 2 over root 3. So if I remember actually what I'm doing with derivatives of inverses, I can do it that way. If you memorize the formula, you can do it this way. Either way, you're fine. What about number 12? It's funny to me, people will miss number 12, and they can find the derivative. Like, watch this. This says, what is the derivative of the inverse of h? Oh, well, I can take the derivative of that. I can find the inverse. Look, switch the x, square both sides, add a 4. So, the derivative, the inverse is just this. So this is telling me to take the derivative and plug a 2 in. So the derivative of this is 2x. So the derivative at 2 is just 4. I didn't even use my inverse stuff, did I? My inverse definition. I just found the inverse. The problem is when you can't find the inverse, we can't do that. We can go the other way, but I can do this. If I can find the inverse, you just rarely can on an AP test. This was very similar to an AP question that popped up the other couple of years ago. And everybody's like, I forgot that formula. I'm like, you didn't need it on this one. Now, let's just assume we did the other way, right? The derivative of the inverse is the same thing as 1 over the derivative of the regular function at 2. Okay? Not at 2. At whatever goes with 2. So, let's figure out what goes with that 2. Remember my answer is 4. So 2 in the inverse would have given me something. That means something in the regular function gives me 2. So right here, if I plug a 2 in there, look, I don't even need to eyeball it. I can solve that. Square both sides, add a 4, you get 8. Or eyeball it, you get 8. Right here, I can tell that x is 8. So 8 is what I'm using. So what's the derivative of h? Bless you. People mess this up because they... Remember, what is the derivative of h right here? What do? Do you remember? The derivative is double it in the denominator, the derivative on the top. So all of that is going here. So 1 over 2 root x minus 4, except you're plugging 8 in. We'll do the math. What do you get? 1 over 2 times square root of 4. 1 over 2 times 2 is 1/4. Flip a 1/4. Back to 4. Y'all seeing these? I hope they kind of all feel the same, but I wanted to link them together for you. And if you forget those formulas for arc sine, arc tan, you can still get away with this. Because this is a way to do all of them. All of them. But if you know the formulas, it just makes for arctan, sine. Those are the two that show up on the AP test. It just makes your life so much easier. And I'm going to be really honest with you. If you don't know those formulas, then when we do integration, it's going to be hard to integrate problems because you're going backwards. Then it really is not hard because it's possible. Because you have to memorize those formulas to be able to go back. Integration is an antiderivative. So, if we're taking a derivative of an inverse function to get here, then we would integrate here to get back to the inverse function. If you don't know the rule, you're out. All right? That's all I got. Somebody asked me about, hey, where are these AP questions you keep asking about? If you just scroll down, you'll start seeing them. They're listed. I believe if you go to the table of contents too, I've marked these so you can see them in your table of contents and find them more quickly. Anyway, or if you pull up the PDF file, if you're on your table of contents and you're, like I have this listed on this book, if you pull up the PDF file, you can just do stuff like this. I don't know if you know this, but I can go click on the 1998, it jumps to it. Kind of nice. If you have the PDF open. All right, that's all I got.